So, thank you very much for coming. I know that it's always difficult to come on the second day, first thing in the morning. So I really appreciate that you're here. Honestly, I think this is going to be an interesting session. It's a session where we are going to mix a bit digitalization, of course, but with the other two pillars that right now we have in the European policy. One of them is sustainability, of course. We will see how some things can help to be more sustainable in the asphalt sector. And also with the third pillar that is quite recent, quite new, and is in the new policy as well of the European Union, the just policy, and is resilience, the resilient economy. We will see a lot of things about how to optimize the maintenance, the inspections, how to make the infrastructure more durable, etc., etc. So I think it's a very good combination that we have today. So, since we are already a bit late, I will start, because if you have seen in the program, I'm actually the first speaker. So, let's see if I have my slides. Should I just go? And there we go, yeah. So basically, in my presentation, I want to show you or to present this document. This is, how I said, is a bit our bestseller at the moment. We published this in June, 4 or 5 different publications. And this one is, at the moment, as I said, the bestseller. It's, I have here. Oh, why is this not? It's in this button, right? Sorry. It's not, isn't true. So we have a little problem moving the slides. Now it's working? Please. Or it's still not. We just do a week. Anyway, well, we'll fix that. So this is a document that is the result of, let's see if now, now it works. It's a document that we published in June during the ENE Congress, and is the result of the work of one of our committees in EAPA, the Health, Safety and Environment Committee, and that comes after as a response to the European objectives that we have nowadays of decarbonization. I'm sure that you all know about the European Green Deal that is already 5 years old, and all these objectives of reducing our greenhouse gas emissions at least 55% by 2030, compared to the reference value, which is the emissions that we had in 1990, not nowadays. And then by 2050, the objective is to have net zero emissions, or to be carbon neutral. So this is in general in Europe for all of the society, for all the economy, but we did our homework to see how the asphalt sector can do what we need to do to make sure that we meet these objectives. So to do that, to establish this roadmap, we did a 5-step approach, methodology. So first was to see where we were in 1990, what were the emissions in 1990, where are we now, what are the emissions now, where do we need to be in 2030 and in 2050. Then we analyzed the decarbonization potential of different technologies, from, let's say, what happens if I increase the RAP content in the mix, or what happens if I produce more percentage of my production at low temperature, more warm mix asphalt, or if I replace the binder with an alternative binder or a low carbon binder, etc., etc. So we analyzed the decarbonization potential of different technologies. And then, by knowing where we are, where we need to be, and the decarbonization potential of different technologies, we established a roadmap, which is a combination of levels of implementation of different technologies that, as a result, give us a reduction in emissions enough to meet the objectives. The impacts that we consider, we follow the environmental product declarations methodology. So we consider the impacts all over the service life of the pavement, of asphalt, from the manufacturing of the raw materials to the transport to the asphalt plant, the impacts at the asphalt plant, the transport of the asphalt to the job site, the impacts in the job site, the installation, And then the impacts also at the end of life. So the deconstruction, the processing of the reclaimed asphalt, everything also at the end of life. What we haven't included, and is because at the moment we don't have yet provisions about the impacts of the use stage, so impacts of maintenance, service life, and all these kind of things. This we haven't included in this study. And it's a pity because honestly, I think that digitalization is where one of the areas where it could contribute the most. Have pavements that have more quality, so extended service life, and optimized or reduced maintenance and optimized maintenance. For example, with the technologies like we saw from XOUBA, for example, how to use the data from vehicles to optimize the maintenance. So all these kind of impacts are doing the service life in the EPD terminologies, the modules B. And unfortunately, we couldn't include it here. Still, we will see that digitalization, digital technologies still can help in other areas of this service life. So something important is that at the moment, the results show that the production of asphalt mix, so up to the gate of the asphalt plant, in order to produce 1 ton of asphalt, average in Europe, we need to produce around 50-55 kilos of CO2. And if we include the impacts beyond the asphalt plant, so the transport, installation, and end of life, then we are around this value in red there. There is around 65 kilos of CO2 per ton of asphalt. Something important is, if you see, just the modules A1, A2, A3, this cradle to gate, this 50-55 kilos, represent already around 80%, or actually more than 80% of the total CO2 emissions. And this means that everything that we can do to reduce the emissions during the manufacturing and raw materials and everything, this is already going to be tremendously impactful. It's going to be good to reduce emissions. And this is why we focus more on that. So as I said before, knowing where we were, the first column, and where we are now, we see that already we have a reduction of 36% nowadays. And then where we have to be in 2030, we found a combination of levels of implementation. I won't get into a lot of detail because everything is in the document, and I really encourage you to have a look at that. We found a combination of different technologies that are feasible for 2030. For example, here we haven't included use of electric trucks or things like that probably we won't have in just 6 years, or at least not will be the main case in Europe. And then we repeated by 2050, and there we did include more things that we are expecting to happen because it's a longer wait, right? So, and if we see this, again, I won't get into a lot of details, but if we see this, where could the digital technologies impact more on this thing? So what we think is especially to make the asphalt plant more efficient, to make the transport of materials more efficient as well, and to make the operations on site also more efficient. Also, we have this section of other, because our objective was to leave our emissions are in at least 90%, because we consider that there will be a 10% that will be covered by other things that we haven't included in this study, but that will happen also over this time. For example, the reduction of emissions to produce electricity or this kind of thing. So it's not something that we will do in the asphalt plant, but it will happen somehow, and it will help to that. So digitalization also have potential to act in this. This is the roadmap. I invite you to have a look at that. So this is how in different years the levels of implementation of different technologies. And at the end of the document, you will also find, for example, some sections where we say that, okay, there are impacts that the road can produce and that we cannot show in the EPD. For example, we know that through maintenance or the selection of an optimized low rolling resistant surface for the pavements, we can actually reduce the emissions from the cars. So this is not something that we will show in our EPD because it's not the emissions coming from asphalt, but it's something that can contribute to decarbonize other sectors, like is the transport sector, one of the most emitting sectors, by the way. And we also have a call for stakeholders to help us to do that. So it's a call for ourselves, for the industry, to develop a series of things. A call for the administrations, and here we talk about regulations, standards, share risks, share responsibilities, green public procurement, all these kind of things. and then also a call to other third parties, for example, to decarbonize the energy production, to decarbonize the transport. We need decarbonized vehicles for the transport, for example, or to supply raw materials that have lower impact. So from the binders to aggregates, et cetera, et cetera. So I invite you to have a look at that. We have quite a few copies in the booth downstairs. So you want to have a physical copy. Otherwise, you can just go on the website and download it for free, like the other documents. And before finishing my presentation, I also want to show you that this is not the only thing that we have done related to the topic of ASPHALT 4.0. This is a document already have a couple of years that we published. It's a classification of roads depending on the support that they can give to autonomous vehicles and electric vehicles. We also have these two that is also is more related to the durability, but we have identified certain impacts of electric cars and autonomous vehicles that can impact on the durability of the roads. So how we need to adapt our roads to make sure that these new users, these new road users, will not affect the durability. We have videos on our YouTube channel, one, for example, on what is ASPHALT 4.0, another one on how to adapt these roads to the new users. And just a couple of weeks ago, I think many of you, because I was talking to many people, that we had this live webinar, and that the video is still on our YouTube channel. I also invite you to have a look if you haven't done it yet. The idea was a bit that if this conference was the movie, this was the trailer of the movie, so it's kind of a teaser to show a bit what we will expect in this conference, and it's working really well. Last time I checked this morning, this video had already more than 2,400 views. So this shows that it's actually a very interesting topic for people and for the sector. It's working very well, and I encourage you also to have a look to this and the rest of the content. And last but not least, I want to show you, this is a draft. It's not published yet, but it's a document that we will publish on ASPHALT 4.0, literally that. So from the definition to all the compendium of technologies, from the asphalt plant to the transport to all the logistics to the maintenance, everything, all the technologies available at the moment will be there, together with some other more philosophical questions. And this, hopefully, we will approve it soon in our committee of ASPHALT 4.0. We have the meeting in October. Hopefully, we will have it. And maybe for the next edition of the ICA 4.0, maybe next year, I can present this for all of you. Thank you very much. And again, this is the link for the document on net zero, if you're interested. But I encourage you to go to our website and just have a look at everything. Okay. See ya. So is there any question before I move on to the next speaker? Not at the moment? Okay. So maybe we have some time at the end. We can just come back to questions. Then I will move to the next speaker. His name is Rok Vezočnik. I think I pronounced good enough. He has a PhD on geodetic engineering and over 10 years of experience with precise remote sensing technologies. His technical expertise includes areas of active, laser, and passive photogrammetric measuring systems, focusing on topics of deformation monitoring, reverse engineering, simulation of static and dynamic processes, calibration of measuring systems, standardization of measuring principles, 3D modeling, and BIM, among other things. So Rok, he's going to present surface-wise road geometry assessment using terrestrial laser scanning. So please, Rok, the floor is yours. So just the green button to change the okay.
So thank you very much for this introduction, and good morning to everyone. So today I want to present this short example in which one of the, let's say, remote sensing modern technologies was used to assess road geometry, namely the unevenness and how it develops around the surface of the road. So traditionally, not to be too long, traditionally the road geometry is measured with a standardized approach with such a mobile platform which contains an odometer, an angular transformer, and the accelerometer. These three, let's say, components usually serve to calculate the ERI factor, so the roughness index, but they can also be used to estimate or to calculate the profile along the road, so longitudinal profile. So this is a one-dimensional approach, but the platform is moving, so we can do it also under under traffic. Compared to this, let's say 1D approach, I call it, there is this relatively, I should say, new, maybe developed in the last 10 to 15 years, laser scanning, or you may know it by this abbreviation LiDAR approach, which uses an instrument which has its own lighting source. It does not require an ambient light source such as the sun or anything else. It can also operate in total darkness. So basically it works like this, that on the left side you can see the instrument. It has a laser source. I don't know whether this pointer can be shown, but the smaller red square is the laser source, and then the laser emits different pulses, and through the very sophisticated mirroring and rotating, let's say, platform, these impulses are sent out into the environment, reflected, and then returned back to the instrument. And this is done very fast, and the instrument measures a huge amount of spatial points, and it then measures spatial angles and the distance to the object. And with such an instrument, one can obtain a very precise, dense, let's say, a huge amount of points, which we call point cloud. On the right side, you can see an example of, let's say, zoom in on a road surface with all the bumps. This is not a point cloud, it's a mesh, actually. It's a triangulated mesh, which was obtained by this type of system. And the pipeline of laser scanning, data capture and processing can be, let's say, split into this very rough steps. So field measurements, and which somehow with which we obtain the point cloud, is very automated these days. You don't need much to carry out the field survey, and what you need to assess the road unevenness is basically the X, Y, and Z coordinates. Additionally, the instruments also measure the intensity of light and the RGB values if the instrument has a camera on top of it or inside. So these are all information that you can get within a couple of minutes. And then the next three steps, which are on the right, synchronization and transformation, filtering, and surface modeling, are not so well automated. They need, let's say, human intervention. And with synchronization and transformation, I refer to the fact that these instruments are not able to see behind the obstacles. That means that you have to place additional stations with the instrument in order to completely cover an object that you are investigating. And this synchronization is somehow referring to the fact that you have to then synchronize these different locations within one common coordinate frame, and then you place it in the final coordinate frame, let's say some local coordinate frame, or even the one that individual countries use. And then filtering is the next big step, very active field of research, in which the result of this step is that you remove the points that you don't need and you keep the ones that you need. So then the surface model is basically just the transformation from the point level to the, let's say, surface level. Optimization is then let's say, the final step, where you decide what level of details you keep, and this is all connected with the the number of points and the file size problems which are related to this big, let's say, this big field campaigns, but this can all be done in post-processing mode, depending on what you want to achieve. And in this short presentation, I want to also tell you that we carried out a small test very close here to Ljubljana, in which we measured a small section above the bridge with the traditional profiler. You can see the 6, let's say, black lines. These are the lines in which the inertial profiler was measuring the road. And then we also scanned this area from 4 different locations, which are seen here with blue dots, to combine different locations. These 4 different locations, we used retroreflective targets. This is standardized equipment. And we chose the highest density with this Regal instrument, which was available. This is quite an old experiment. Nowadays, you can have instruments that are able to produce even denser point clouds than this one. But the density that we chose was 7 millimeters in both directions at the distance of 10 meters, just to give you an idea. And the whole campaign took half an hour, including the drive with the profiler. And our aim was to see whether this terrestrial laser scanning, being a surface-wise approach, can be beneficial compared to the, let's say, one-dimensional inertial profiler. Whoops. So from the laser scanning point cloud, we first did the steps which I already described. So we placed the point cloud in the coordinate frame. We filtered out the traffic because this was done under the traffic. So we had to filter out the cars and all the silhouettes that the traffic was producing. And then we transformed the point model into the surface model, and we simply put the planar model through the point cloud to see what the unevenness, let's say, level was like. And we clearly, on this image, you can see, where's the pointer is here. So these are, I don't know how is it from the back, but these are the route, let's say, lines. So clearly this road was quite damaged because the deviations from the plane were around plus or minus 3 centimeters. So it was quite easy to detect them, and they make sense because they're all along the driving directions. And then in these, let's say, 6 lines where we also had measurements from the inertial profiler, we tried to compare the results from the scanning and the traditional approach. And what we found is that most of the deviations were within, so here, this graph shows on the right side, you can see the differences between the profiles in, let's say, one particular lane between the laser scanning and the inertial profile. So this is this blue line. Most of the differences are below 5 millimeters, and 5 millimeters was the accuracy level for these instruments, which means that we're quite good with the results. And the spikes which go beyond 5 millimeter level are actually the result of the profile not being able to follow straight lines. So these were not, let's say, some errors produced by the laser scanning. It was more like this ability to synchronize one system results with the other. And we found that similar results could be found for all the rest 6 profiles. So I only show here one profile. And based on these results, we have decided that it's quite useful to have this kind of surface, full surface coverage results, because they are quite reliable, and they can be used for different applications. For example, for some complex simulations, one of which I show here with the reference. We produced an article which used this very precise road model from the laser scanning in simulations of how the vehicle crosses a bridge, and how, because the bridge is equipped with sensors, it also measures the response of the bridge when the vehicle is passing over. And this simulation was done not with a, let's say, very simple road model, but with this kind of sophisticated model. So I think that in the end we have somehow managed to show that for shorter, let's say, road sections, because this is a static laser scanning, such models can be used not only to be let's say, in the same quality category with inertial profiler, but they could also be an advantage when trying to perform, let's say, more high-level tasks or comparisons of monitoring road geometry. So that's my talk, I guess. If you have some questions, I will gladly answer them. Otherwise, I don't want to be too long, because I think we're supposed to be 10 minutes or so, right?
Yes. Is there any question? Please. Is that sorry? No questions? Okay. Okay. Well, maybe Andrew can have some time.
Okay. Okay.
All right, so our next speaker is Miguel Muñoz. You already know him because he was presenting yesterday. Still, I will say a few words just in case you missed the presentation yesterday. He's a civil engineer and data science graduate. His career has been focused on the intersection of road safety, vehicle data, and real-time traffic information. And some information that maybe you don't know about him, some inside information, is that he is also an elite archer. So he has won many competitions, but still I think he didn't bring any arrows. So don't be afraid of asking difficult questions anyway. So please, Miguel.
Thank you. Here am I again, but that time is not for me, the presentation. It was for Camino. Camino Arce is the technical director of CEIT. That is an entity that I speak already yesterday, but today we are going to focus a little bit more on that company. So we are, the title is really difficult, but as the project is, so we are assessing the impact of road roughness improvement on emissions and fuel consumption using connected vehicle data. Okay, so basically what we're trying to achieve is, with best roughness of the road, is gonna use less fuels, so we are gonna make less emissions. As Ralph says yesterday, that we need to show our job, that we are making the road safer, less contaminant. That's a good way to let the people know that what we do when we make roadworks, everybody gets angry because they are stopped. That is for something really good and really good for the planet. So CEIT is a state-owned public company set up in 2005 by the Ministry of Transportation, but it works completely different from the ministry. It has his own resources, his own network, and they collaborate a lot, but they are like another company, another part of the ministry. In 2019, CEIT became the Spanish toll road maintenance company with the largest number of kilometers under its responsibility. Okay, so it's the biggest company that has the roads. So, as I told yesterday, CEIT has 9 toll highways with almost 500 kilometers. and 14 associated free motorways with 2,015 kilometers. That's really low compared to the ministry that has 26,000 kilometers, but there is plenty of traffic in those roads, so they are really important. As you can see on the map, maybe some of you don't know Spain, but Madrid's in the center. There is plenty of traffic in Madrid area, and it's the center of the economy, actually. And also in the east, because of the corridor of the Mediterranean corridor, and it's really important for that. So they are making right now a huge investment, really, really huge. They are making a good effort with almost 400 millions of euros, where almost 60% are for payments. That's a huge amount in this network. There are also investment in tunnels, structures, lining, and other things that are working on it. So the project that we are already doing is in the M50. It's a ring around Madrid. It's not close yet, at least. It's around the south part. And as you can see, 85 kilometers, and the AADT is almost 100,000. That's plenty of traffic. If any of you go to Madrid, you will see that there's plenty of traffic, a lot of traffic jams in the morning and in the evenings. So people travel to the job and to their houses. So it's a really important network. So what is the process of this project? First of all, this summer they made the payment works. So we have first to segment the road, then the data collection. Well, technically the data is in the cloud, so we only have to access to the data. Then we have to estimate the fuel consumption and CO2 emissions. We tell estimation because we don't have the complete fleet, but when you have the data, you calculate, you don't estimate. So we calculate of the bias that we have. We are collaborating with the traffic Spanish entity, DGT. They put some traffic counts with when they read the plates of the cars. So we know the ground truth. So technically, we know the real traffic of the roads. And also we know the type of engines that they have, if they are hybrid, petrol, electric cars. So we have the bias, that is our connected vehicle data, and we have the ground truth. So we can compare what is happening in one way and another. Then we make the analysis, and finally the before and after comparison. Sadly, they finished the works less than a month come here, so we don't have the after results, but we hope that are going to be really good. But so we are gonna focus on the before analysis. Well, this room is too big. Maybe at the back you don't see the graphs, but let me explain you. The top heat map is the fuel consumption in milliliters per hectometer. So the connected vehicle data gives a lot of information, as I mentioned yesterday, and now we have a really cool one, that is how much fuel of any type, it can be electric, that we are gonna separate from this study, but we have if it's hybrid, if it's petrol, of what type of car, if it's a light car, a truck, we know all those things. And also we know the emission that the car is really making. Europe is making a huge effort to know the emissions, and the cars know what are the emissions of each moment. So when you accelerate a lot, you are making the world a little bit dark, but we are trying to achieve that. And then in the lower part, we have the speeds. So I think that most of you will see where we have less speed, we have more greenhouse emissions of gas. Also, we have more consumption. When we go faster, it depends. I'm going to make some assumptions, but when we go faster, we have less fuel consumption, so we make less greenhouse gas emissions. Okay, so this is the part that is coming from the car. So as the road manager, you cannot change that. The cars are where they are. The speed the people is going, you can limit the top speed, but when there is a traffic jam, you cannot tell, no, go faster. They want to go faster, but it's impossible. So that's the car information. That's the ground truth that we have in a bias. In not all the cars we have the information, but at least we have what is really happening. We don't make any calculation or estimation on the fuel consumption or in the greenhouse gas emissions. Then the part that we can work on is the roughness, the surface. So that was the IRI, let me say almost IRI. We don't want to fight in that battle, but this is going in each direction. You can see where is the IRI really good, that is almost 0, and where is really bad, let's call it, that is over 2. That's not a lot, but like there is a highway and plenty of traffic, we are making the comparison. So we are in August. They have finished this work. In the next workshop, I can show you how it is paved and how it improves the roughness of the road. But this is the after. Okay, so they did a really good job with ASPHALT that we are working in this project. They make in August a big effort to make this the better they could. So the objective of the project is to evaluate the environmental impact of repavement. They are making a huge investment, and it's not only for the comfort, for the traffic jam, for the safety, if it's also for the emissions. That is the topic that we are already focused. And the good thing is that we are really having a calculation on the real truth that I think in this room, everybody thinks that a better road make less emissions. So we are making the calculations on it. The insight so far is that traffic, speed, and emissions are very correlated. As you can see in the last graph, we are not having anything in charge of geometry of the road because it's not changing. So that's something stable, and we're not making a study in that. And the expected results are improvement pavement condition leads to reduce greenhouse emissions. That's the objective. Also, if we improve that, we are making less travel times because the speed is gonna be higher, but not too much higher, just a wave of people travel at the same speed. So when people are traveling at the same speed, there's no traffic jams, there are less accidents. So that's another way that we're gonna try to achieve or to study what is happening on the road. So thank you. I'm open for questions. Don't be too bad, and thank you so much.
This is good. Any question, anybody?
No questions for Miguel? Please. I don't know if, yes.
Thank you. Thank you for a great presentation. I just had a question on how you measure fuel consumption. Is it a special vehicle, or do you just hack into the regular car?
Yeah, we get into a regular car. Our car is connected. It sends your location, your speed, your wipers, your, I don't know which radio are you hearing. So it also sends the sum of the car, not all of them, the fuel consumption that you are making in the moment, and also the emission that you are making at the moment. So we have a point, depending on the provider, but 3, 5, 10 seconds. So we interpolate and we make the trace of the car.
Okay. And another question, have you tried correlating it to noise levels?
Not yet. We will make it, but we are focused only on roughness.
Okay. Thank you.
Any other question? Because I actually do have a question after seeing the first two presentations. We are seeing like two different approaches. On the one hand, we see one very accurate measure done by a laser on a specific road section. On the other hand, we have like an estimation of the IRI based more on big data, not so accurate, but it's more an estimation based on the data coming from vehicles, but with that we can cover a big network and do it more in monitor like real time. And so it's like opposite approaches. And my question is that will we need only one in the future? Will we need both? It will be complementary. I don't know how the speakers think about it, or also people in the room. So maybe we start with you since you are there. But
Yes, I think both, because I have the macro situation. I'm not focused on really specific problems that maybe in a bridge you need to really have a look close of what is happening. But in such a big network, for example, in Spain, it's impossible to measure really, really close every segment on the road. Also, I have daily update that is really powerful. So it's really complementary and we need both.
yes.
And my opinion is both. I absolutely agree with you. But evidently, it's a pseudo-IRI. It's not exactly IRI, it's pseudo-IRI. But for me, the most important thing, you have the possibility to verify the evolution of the IRI based on big data, the trends. And this is evidently is another level. The accurate, the measure, evidently is the new systems based on that. But to have at the same time all the network and to have the trend, to have the evolution, I feel is necessary to have both information, complementary.
Would you want to add something?
I think I just want to join what the other two have said. I think that the good thing today is that you can combine different technologies. So then depends whether it's a national level or it's a very small location with very precise, let's say, parameter that you have to estimate. But in general, it's nowadays we are at the level where we have this, let's say, advantage that we can combine data and we can combine also sensors. And as long as we know what we want, it's technologies at hand. So I think combination is the future, absolutely.
Okay. So glad to see we're all on the same page. Thank you, Miguel. Thank you very much. And our next speaker is Andrej Anžlin, as I hope this is the right pronunciation. Head of a section of bridges at SAC, is structural engineering with a PhD on seismic engineering. Since joining SAC in 2011, he has always tried to make unique contributions to bridge engineering. He has a vast spectrum of experience, including roles on bridge inspection, as a bridge inspector, involvement in numerous research projects, experimental work, and field monitoring. He has also served as a guest researcher at the University of Zagreb. In his current role, he is focused on innovative solutions in digital bridge inspection, structural health monitoring, and bridge structural safety analysis. It is enriched by his diverse background. So, I explain you.
So, hello everybody. It's really, I'm really blessed that today I could come to this event by bike from the home office. It's a rare occasions I can do that. So, let's dig into today's discussion, or the way I see it today. I will share some of our experience on our section for bridges, and also on top of that, I'll try to put some my point of view on the digitalization in general. So, because I'm an expert in structural engineering, I will say just a few words about the bridge or the bridges, and say a few motivational information. So, bridges are rapidly aging, and Slovenia is no exception. So, for example, by the end of this decade in Slovenia, nearly 40% of bridges will be more than 50 years old. And 50 years is a milestone in the designing of the bridge. So it's really good to know what the future will come will deliver us in that sense. Then, of course, the traffic, it's something that we are experiencing. Traffic is growing, and if only a half of these future speculations about the growth of the traffic will come true, I cannot imagine how I'll commute to Ljubljana or you to your places, wherever is your situation. So now I'd like to share the way I see the bridge operator has, let's say, a mission. So ideally, he wants to improve, and then when he sets his goal, maintain the overall condition of the bridge network he's responsible for. And the question is, what is a good bridge? And how can we measure what is good? And lastly, when do I need to act? And here I will show you, this is a really old currency nowadays. It's Slovenian tolar. So we never have enough money. Even the richest countries in the world do not have enough money to maintain their infrastructure. So this is de facto. And this is one of the rare occasions you can see the President Biden from his back. And imagine this is a picture taken a few hours after the event, because he was giving some speech about the good infrastructure in America. So imagine, what would you do in this situation? It's really the reactive response of all the responsible people is on a different level. So my idea here is to show that you are prepared, but not for this, but to prevent this. And I have started showing this picture 2 years ago. So the way I see bridge assessment can be linked with 3 really important characters in this process. And I really like to show this because I'm sure that a lot of people have seen this blockbuster that is a hangover movie. And here are 3 interesting characters. And each of them is not so interesting as their interaction and combination within the movie. And this is the same how I see the bridge assessment process and what is the ideal trio. Okay, so the first thing is the bridge inspector or the bridge inspection. This is the first front line to get information about the quality of the structure, in our case, the bridge. And that is, let's say, the leader of that bridge assessment process. And if that leader identified that something is not going right, he then prescribes monitoring. Just making pictures of some damage every month is already a monitoring by my definition. But monitoring can be really complicated, as is this guy in the movie. In the end, ultimately, we do some reliability structural analysis. And I would like to point out that the concept of this analysis is completely different to when you design a structure or when you assess. Okay? So this is really a tricky part. But of course, the title of presentation is the digital inspection. So let's focus on the first guy. Here is a movie showing our, let's say, first experience nearly 4 years ago about how to use some digital data and to extract the information. The way we were faced with different projects, I can list here a few bullets which are, let's say, relatively in line with the digital bridge inspection. These are drones, digital twin technology, BIM, AI, and non-destructive evaluation. This is something that is really old. And of course, sensors and cloud computing. So by some definitions, all these technologies or solutions can go into the bucket of digital bridge inspection. But let's say a few words about how it is in Slovenia and what is our experience. So the traditional inspection, the way we feel it has the biggest, let's say, issue is creating some traffic delays because of our process. So we need to have partial closures, and people are not happy when you have closures, right? Because it's just additional commuting time. So the way I understand, when people do not know anything about bridges, then our work is very nicely done, okay? So when the people are aware there are bridges, then something is wrong. But in digital inspection, let's say, the idea was that we try to use drones and to see how can they be applied to our current solutions. And we, let's say, successfully completed 3 development projects financed by Slovenia Motorway Company and Slovenia Infrastructure Agency. And we started in 2018 with the first project. We started in the lab, and then we go into the field. And in the lab, we produced some mock-up concrete box where we simulated the lamination of the concrete cover. We used thermal cameras to see how can we detect this kind of damages. We also simulated the cracks and used some AI machine learning algorithms to, let's say, detect cracks on that kind of concrete blocks. Of course, the real bridges are something completely different. So we have experience from 7 case studies from the bridges in Slovenia, where we focused on the concrete structures. So these are 3 the most, let's say, usual damages: cracks, delamination, and corrosion. And the idea was to look at the traditional inspection and also find what is currently, at that time, of course, the best digital inspection upgrade that can be a compromise between the cost and the effectiveness. In the end, we, together with contractors, proposed some guidelines, what is the next step, how to proceed in the near future. So here are some photos of models with damages, and in the end, we did some cost-benefit analysis. If we only concluded direct costs, it's really important to also consider what is the future. But if we would also calculate indirect cost, the solution is now already, it makes sense to use it. So this is regarding the digital bridge inspection. Now let's say a few words about the development. This is my personal opinion. It's not something that is opinion of our institute, but I would like to read out this quote from Benjamin Franklin. So, it takes many good deeds to build a good reputation, and only one bad one to lose it. Okay? And in the sense of embracing any digital transformation, I think that each of us had some bad experience and some good experience, right? If it's banking or maybe healthcare system, and our industry is no exception. So during these projects and also other projects that have not been mentioned here, I have here listed a few challenges, and such as complexity and integration, security and privacy, cost and funding, adaptation and training. So this is really important to think about when you try to make some changes, okay? So I would like to use an opportunity here to talk about how we can make a change. So what are the drivers? So policy and regulation, financial incentives, and cultural acceptance. So I hope that after today's talk, somebody will reach out to me and we can have a discussion about how to embrace digital bridge inspection. Okay, so I was told that in the end, the maximum 2 takeaways are enough to conclude, because people have a limited capacity of remembering something. And I really thought about it, what would be the 2 takeaways regarding the digital bridge inspection. So one thing is gradual implementation and careful consideration. So all parties involved in any kind of process of digitalizations have to be involved and honest about what are the expectations and what are our goals. And we have to earn decision makers' trust, because hopefully or ultimately we will be able to have different approaches in the future, which will become standard practice. Okay, that's it from my side, and I'm really looking forward for any questions.
Questions? No questions at the moment, so thank you very much. And maybe
There is, I think, one.
there's one there? Okay, sorry.
Thank you very much for these nice presentations, but I want to point out, we find out that there are problems on the road or on the bridges, but the main thing is to create the reaction to that. And this is what's lacking. You know, in Germany, some weeks ago, there was a bridge over the Elbe that collapsed, and it was obvious that this bridge had to be maintained, but politics did not decide to do so. So this was why that bridge collapsed. And the most important thing to me is we collect all that information, we do it digitally, we show that we need funding, but we have to keep the pressure high to get a reaction to that. All the data don't help when the bridge collapses at the end. So this is the most important point to me. Not a question, but a statement.
Good. Yeah. You want to add something to that? You agree? Yes.
I was wondering, how would you comment? What has the situation, let's say, in the last 5 years, also in Slovenia, changed in respect to the level of trust into the digital, let's say, approach for bridge monitoring? Has it increased a lot, or is it going slowly? What would be your, let's say, comment on this in the last 5 years?
Yeah, I think it's gradual.
Right.
It's gradually growing, but that's just my point of view. Maybe you should ask also stakeholders, other stakeholders and other parties involved. Yeah, I think that we are shifting step by step, and it makes sense. Of course, I would like to speed up the process, but if I respond to your comment, yeah, that is our big picture, big goal. That's why we're doing this. Yeah, but the important thing is also, I think, to understand why they, in this case, have not make a response. I'm sure that everybody would like to do something, but I think it's really important to point out what I have said before. There is not enough money. Never will be enough. So we have to make a smart decisions. Yeah.
Don't see it like, sorry.
That's what discussion is about. Yeah.
Sorry, it's always a struggle about the funds. There is enough money, but we spend it in our societies not to our purposes, but to the purposes of those who cry the loudest. So we have to be louder. Our branch has to be louder. We have to tell the traffic people, those who use the roads, you have the right to have a good road. You have a right to have a secure bridge. And it's not acceptable. We are not loud enough. This is my statement. So there is money, but we have to struggle to get it. It's a fight for division of the funds, and that's it. And we are not loud enough, that's it.
Wow.
Yeah, if I may to respond to that, yeah. I agree. I agree there is enough money. But let's just make one scenario. Let's have all the money that we want to have. You don't even have our resources to spend the money, to realize that. So it's not so just like money will save everything, but I agree that we have to compete with also other parties in the government and try to, the politics is about to have the best compromise, of course.
Okay, well, great discussion. So let's move on then to the last speaker. Thank you very much again for this presentation. Here better? Yes. The last speaker is Martin Hauptman. He's a project manager at CESTEL, the Slovenian producer of bridge weight in motion systems. He mainly works on CESTEL's projects in foreign markets. Today, he will present a case study based on over 20 years of bridge WIM measurements in Slovenia.
Hi to everyone. Hi to everyone. My name is Martin Hauptman. I'm coming from the company CESTEL. We are, like I said, like it was said in presentation, producers of bridge vane motion systems. And today I will present to you vane motion measurements that we do in Slovenia, that we have been doing in Slovenia for the past 20 years. This presentation was prepared in collaboration with Mr. Miloš Dular. He's the head of the Division for Road Maintenance and Traffic Safety at the Slovenian Infrastructure Agency. Okay, so first, a couple of words on the agency itself. So the Slovenian Infrastructure Agency manages Slovenian regional and main roads, as well as the railway networks. If you look at this map over here, you see the thick red lines. This is the motorway network in Slovenia, which is managed by the motorway company in Slovenia. And the rest of these lines, yellow, purple, and green, these are the main and regional roads which connect regional centers in Slovenia. So these are centers of larger centers of population. All in all, there's about 6,000 kilometers of main and regional roads in Slovenia. And now a couple of words about way in motion. So one of the tools that the Slovenian Infrastructure Agency uses to manage their infrastructure are way in motion systems. Now, way in motion systems, generally speaking, are systems which weigh vehicles while they're traveling at their normal speed. So alternative to way in motion systems are, let's say, static measurements of heavy vehicles or low speed way in motion systems. So of course, way in motion systems, we also call them high speed way in motion systems, have a huge advantage against statically weighing vehicles because you can weigh a lot of vehicles if you don't need to stop them. So when we talk about high speed way in motion systems, there are two types of these systems. One type are conventional road way in motion systems or pavement WIM systems. With pavement way in motion systems, the sensors are cut into the pavement. So you need to cut open the pavement, install the sensors inside, and then resurface the pavement. And the second branch of way in motion systems are bridge way in motion systems, where you install the sensors on the bottom side of the bridge. So bridge is in the name of the system, so you basically use the bridge to weigh the vehicles. The advantage of bridge way in motion systems is that these systems are completely portable, and you also gather the data on the bridge itself, so you also gather structural data. Here is just a simplified animation of how these systems work. So a heavy vehicle passes over a bridge. The sensors below the bridge then detect each axle of the vehicle. They detect signal from each axle of the vehicle, and then the algorithm of the system gets the data from those signals and interprets those signals and gets the useful data out of it. In Slovenia, we've been doing bridge way in motion measurements since about the year 2000, and each year we do between 100 and 150 of these measurements. Like I said, bridge way in motion systems are portable, so that's why we can talk about the unit here is measurement. So we do some of the sites that we have in Slovenia are permanent, mainly on the motorway network. But otherwise, the majority of the measurements we do here are temporary measurements, which last anywhere from 6 months to only 1 week in duration. And these dots you see here, these are the measurements that we've written about in our article. This graph shows the most basic data which is useful for infrastructure owner that you get from a way in motion system. This is the percentage of overloaded vehicles. Now, I wanted to show you this graph just so you can see that you can't see anything out of it. Now, this graph was made from 13 sites on our main roads and regional roads. And we've chosen these 13 sites because we had continuous data from the year 2010 to 2023. And as you can see, there's incredible chaos in this graph. So unlike motorways, where the percentage of overloaded vehicles doesn't vary that much, on the main roads, regional roads, and local roads, percentage of overloaded vehicles varies significantly from year to year, from one location to the other location. So I don't know, in 1 year you can have almost 40% of overloaded vehicles, then in the next year it drops to 10%, and then it goes up again. So we have this incredible chaos. Why the situation is like this, I will show you in the later slides. And here is this same graph, but it's a bit cleaned up. So these are linear trend lines. So all in all, you can see that the Slovenian Infrastructure Agency is incredibly successful in reducing the percentage of overloaded vehicles. In 2010, there was about 15% of overloaded vehicles on their roads, at least on these road sections, I should say. And last year, it was about between 10 and 11%. So now we'll take a closer look at the most recent data that we have from 2023. The article that we've written for this presentation was based on 62 measurements, which was one of the projects that we did with the agency. And like I said, these measurements varied in duration from 6 months to 1 week. The majority of these measurements were 1 week in length. And like I said, the most basic data is just the average percentage of overloaded vehicles. And in last year, this percentage was the percentage of overloaded vehicles was 12%. So, like I said, this varies significantly. We had a location near Ljubljana where only 2% of vehicles were overloaded. Then we had a location near one of the industrial centers in Slovenia where almost 28% of vehicles was overloaded. So the percentage varies. And the second concept that now I want to introduce is the traffic loading. This is, in my opinion, the most important piece of data that infrastructure owners get from weighing motion systems. And I will just briefly introduce this concept. So traffic loading is measured with the unit ESAL, which stands for equivalent single axle load. This concept was devised in the United States of America in 1950s when they made a series of road tests where they investigated the connection between axle loads and axle configurations and the road damage. So they introduced the concept of standard axle. And here on the left, you can see standard axle in Slovenia. In Slovenia, this is a single axle with double tires and 100 kilonewtons of axle load. So this axle is by definition defined as 1 ESAL. Now, if this axle had, let's say that 100 kilonewtons equates to 10 tons, but let's say that this axle would have a burden of 15 tons, then it wouldn't cause 1 ESAL of road damage anymore, but it would cause 5 ESALs of road damage. So this same axle, just with a larger axle load, causes 5 times as much damage as it was initially with the 10-ton axle load. This is because the relationship between axle loads and road damage is exponential, as you can see in this graph. And this is, of course, incredibly important for infrastructure owners, because as it turns out, of course, traffic loading is dependent mainly, well, first and foremost, on the number of vehicles. So the larger number of heavy vehicles you have on a road section, the higher the traffic loading will be. But then secondly, of course, it's also very much, as you can see in this graph, it's also connected to the axle loads. So you can have a relatively small number of heavy vehicles, but if a large percentage of these vehicles have overloaded axles, you'll also have quite a large traffic loading. And just for information, in Slovenia, on these 62 sites that we based our article on, the average traffic loading was 543 ESALs per day. So this was average daily traffic loading. Now I wanted to show you two interesting pieces of data from the last year's database. The first road section that I wanted to show was a road section where we detected about 240 heavy vehicles per day on average, and more than 26% of these vehicles were overloaded, which is, of course, a very high percentage. But it turns out that ESALs per day, so daily traffic loading, was not even that high. It's 223 ESALs per day. Now, why did this happen? This happened because this road section has an axle load limitation of 8 tons. So legally speaking, many vehicles here were, it will come back. Legally speaking, many vehicles were overloaded here because vehicles were loaded normally. So they abided by the 10-ton axle load limit, which is on normal roads. But because of the axle load limitation, legally speaking, these vehicles were overloaded. But of course, the axle load limitation on that road section was there for a reason. So this traffic loading is, of course, too high for that road section. The other thing I wanted to point out was something that we in CESTEL, we see this pretty much all across the world. Let's say you have a two-lane road with opposite traffic, and one lane has a substantially larger traffic loading than the other lane. This happens, of course, because you have fully loaded or overloaded vehicles driving in one direction, and then these same vehicles are returning to where they came from empty. Now, the danger here is that if you would have a traffic counter and you would simply count the vehicles which were driving on this road, you would say, okay, we have, I don't know, 200 vehicles per day here, and you would assign to them some theoretical value of traffic loading. But because with the weigh-in-motion system, you can weigh these vehicles, you see that actually these vehicles can be very heavy, and axle loads can be very heavy. So you can have a large discrepancy between theoretical loading and actual loading. And this is what this graph shows. So every year we compile such a graph where we compare real traffic loadings that we detected on our weigh-in-motion sites, and we compare it to the theoretical traffic loading which we find in the technical specifications for design of roads. So if this ratio is 1, this means that the real traffic loads and theoretical traffic loads are the same. But of course, what happens in reality is that in the vast majority of sites, real traffic loadings are much higher than theoretical traffic loadings. In fact, there are, let's say, a couple of sites from the database that we used where the real traffic loading was 4 times higher than the theoretical traffic loading. Now, the result of this is, of course, that road will be damaged or destroyed, if I can say it like that, much sooner than it should be. Now, up until now, we talked about these theoretical concepts, ESALs, and statistics, but I wanted to show you why, in reality, this happens. So I took photos of 3 vehicles that were, our system took photos of 3 vehicles that were driving on these roads. So these 3 vehicles represent very nicely where the problem is. So all of these vehicles are driving on regional and main roads in Slovenia. Well, in fact, you will see these vehicles all across the world. They are severely overloaded because the maximum allowed gross vehicle weight in Slovenia for normal transportation is 40 tons. Of course, they're so severely overloaded that axle loads are also severely across the limit. And such vehicles are the main results why our roads are destroyed. So if you just go a bit more into detail, the first vehicle is a timber lorry. These are very characteristic vehicles in some parts of Slovenia. This is very much seasonal transportation. So what happens is, let's say, for 2 months a year, you will see these vehicles on roads, but then for the rest of the year, there won't be any heavy traffic. So statistically speaking, you would say, okay, we don't have a problem with overloaded vehicles because for much of the year, there is no problem. But in that short period of time, you can have a large number of these vehicles which are very detrimental to the road. The second vehicle is a vehicle from a construction site. This is like a typical vehicle everywhere in the world. These vehicles are very often extremely overloaded. And the third vehicle is an exceptional transport without a permit. So these are also types of vehicles which can be very problematic for the road sections. Just a couple of final thoughts. So I think that I hope I showed that systematic monitoring of heavy vehicles work. The Slovenian Infrastructure Agency managed to decrease the percentage of overloaded vehicles on its road from the year 2000. They had about more than 20% of overloaded vehicles. Now they're closing to about 10%. Now, this is just a simple table, but behind these numbers is a lot of work by people from Slovenian Infrastructure Agency, motorway company in Slovenia. They also cooperate with the Slovenian police, which does the enforcement of overloading. Then I also have to mention, let's say we have the Slovenian Agency for Traffic Safety, which tries to educate the truck drivers and trucking companies on why overloading is bad, because it turns out that many times they simply don't know, they don't have the knowledge on why they shouldn't be driving overloaded vehicles. The second point I want to make was that wherever possible, weigh-in-motion data should be used in road design. Like I said, we at CESTEL, we do measurements all across the world. And I can say that especially in Western Europe, road infrastructure owners are very sure that they don't have a problem on the roads, that there isn't much overloading. But overloading is problematic everywhere in the world. So if you're in Germany, in the Netherlands, or in Indonesia, you have a lot of overloading. And like I said, I hope I showed you through the presentation, Overloading is especially problematic on the roads of lower categories, so on main roads, local roads, regional roads, which have not been designed for high traffic loads. Thank you very much. Thank you.
So, any final question? Yes, there's one.
But not. There's one at the end. I don't know. Yes, have it. Good.
Hello. Hello. I would like to ask you if you can tell me the accuracy of measurement in percentage. Then if this technology can be used in industry, and if you can maybe say something about technology which is used and how the measurement is done.
Okay, yeah. So the accuracy levels are, so we usually say that the accuracy that we achieve is usually between 5 and 10%. It a bit depends on the quality of road surface and the quality of the bridge, but we are in the range, like I said, between 5 and 10%. That's the first question. How the system works. So the sensors that we use are strain gauge sensors. We, like you saw on that photo, we fasten them, we screw them on the bottom side of the bridge. If it's a concrete bridge, if it's a steel bridge, we glue them to the bottom side of the bridge. And then through the difference in the voltage in the sensor, the algorithm interprets that signal and sort of gets you useful data. For the last question regarding the use of data in industry, I mean use of our systems in industry, we can talk about this after that, but I would have to know what you have in mind. But our systems have been used, let's say, in ports to weigh traffic that goes in and out of ports. They've been used in several of such, let's say, special cases. But okay, we can have a discussion later. Yeah.
Okay, thank you. I think it's a very interesting study. To be honest, we are seeing all across Europe that the loads are increasing, and now we are not even speaking about electric cars and these kind of things that also tend to do it as well. We are seeing these super single tires, more pressure. We are seeing pressure from the automotive industry to have these large trucks, these road trains that have a lot of advantages in terms of emissions and the need for drivers and traffic congestion. But at the end, either we increase the load per axle, or even if we increase the number of axles to distribute the load, it might be a problem, because something that we have in our documents, asphalt is a viscoelastic plastic material. So when you have a series of loads exactly on the same point of the cross section and with very short recovering time in between, that can create some kind of permanent deformation. So this is a very important issue, the loads and so on, that we are also monitoring, and I appreciate that you have this
Thank
kind
you.
of. Thank you. So thank you very much. We're a bit late. Thank you. So I would propose that we have a 10 minutes break. We resume around 10:35, and we have a workshop that I think is going to be very interesting as well, where we can see live how different companies are introducing the data in different tools, how to use it, how to do the analysis of the data. So I think it's very practical, and it's going to be very interesting. So let's say 10 minutes, and we resume back. Thank you.
Perfect. That's it.